Hey everyone! Today we're going to dive into one of the biggest questions in science. We're going on a journey, really a kind of detective story, to figure out what an atom, the tiny building block of, well, everything, actually looks like. So that's the big question, right? If you could just shrink down, way, way down, what would you even see? A tiny solid ball? A miniature solar system? Well, the answer has changed a ton over the years, and the picture we have now is stranger and frankly way cooler than you might imagine. Okay, so let's start at the beginning. For a really, really long time, the best guess was pretty simple. Scientists thought of the atom as just a tiny, solid, indivisible sphere, like a microscopic billiard ball. It was a neat, tidy idea and it worked for a while, but that simple picture was about to get completely shattered. The whole game changed when scientists figured out a way to crack that supposedly indivisible sphere open. And guess what? They found it was made of even smaller, more fundamental pieces. And this is where the story of the atom starts to get really interesting. So let's meet the first new character in our story, the electron. This little guy discovered by Thomson has a negative electric charge, and finding it was a huge deal. It was the very first proof that atoms had an internal structure. But, as it always goes in science, this amazing discovery immediately created a brand new puzzle. I mean, just think about it. If atoms are packed with these negative little bits, why isn't everything around us buzzing with electricity? Why is your desk, your chair, why are you electrically neutral? It just didn't add up. Logically, there had to be something else inside the atom, something positive to balance it all out. And there it is, the proton. This particle has a positive charge that perfectly cancels out the electron's negative one. Okay, so now the scientists had their ingredients, positive protons, negative electrons. The next huge challenge was to figure out how they were all arranged. What was the blueprint? And this kicked off a thrilling, high-speed race to draw the first real picture of the atom. A whole bunch of different models were thrown out there, one right after the other, with each new idea either building on the last one or just completely demolishing it. Thomson himself took the first crack at it. He imagined the atom as something he called plum pudding. You just picture a big ball of positive pudding with the negative little electrons scattered all through it like plums. You know, for a first guess, it's pretty logical, but it wasn't going to last long. What's just incredible here is how fast all this happened. Just 7 years after the plum pudding model, Ernest Rutherford did this legendary experiment. He fired tiny positive particles at a super thin sheet of gold foil. He expected them all to just pass right through the pudding, but some of them bounced straight back. He famously said it was as surprising as firing a cannonball at a piece of tissue paper and having it come back and hit you. This result was totally impossible with the plum pudding model. Rutherford came to a conclusion that was just mind-blowing. The atom, he realized, is over 99.9% empty space. All the positive charge and pretty much all the mass was jammed into this impossibly tiny dense center he called the nucleus. The little electrons, they were just orbiting somewhere way out in that vast emptiness. This was a completely new picture of matter. But see, Rutherford's model had a huge flaw. According to the physics of the time, an orbiting electron should constantly lose energy and spiral down into the nucleus, causing the atom to collapse in an instant. Obviously, that doesn't happen. So along came a physicist named Niels Bohr who proposed a brilliant, kind of wild solution. He said electrons can only exist in specific fixed energy levels, like planets locked into their orbits. You can think of it like a ladder. You can stand on one rung or the next rung up, but you can't just float in between. Bohr's model was a massive step forward, but it still wasn't the final answer. To really understand the atom, science had to let go of those nice, predictable orbits and take a leap into the strange, probabilistic world of quantum mechanics. And this, my friends, is where things get really weird. This whole revolution started with a core idea from Max Planck. He discovered that energy isn't smooth and continuous, like a ramp. Nope, it comes in tiny, distinct packets called quanta. It really is like a staircase. You can be on one step or the next, but you can't be on step 1.5. This single idea would completely reshape our understanding of what an electron even is. And that brings us to the modern view. We don't talk about an electron's orbit anymore. Instead, we call it an orbital. And an orbital isn't a neat path. It's a three-dimensional cloud of probability. It's basically a map of where the electron is most likely to be found at any given moment. We had to trade the comfort of knowing exactly where it is for the strange elegance of probability. Now, a probability cloud might sound messy and random, right? But it's actually governed by a very strict set of rules. See, we can't know exactly where an electron is, but we can describe its state with incredible precision. We do this using a set of 4 quantum numbers. And you can think of them like a cosmic home address for every single electron. So here's how that address works. The first number tells you the mean energy level. That's like the state you live in. The second number defines the shape of the orbital, which is like the city. The third number describes that orbital's orientation in space, kind of like the street. And the fourth number is the electron's spin, either up or down. That's the house number. Put it all together, and every single electron gets its own unique identity. And electrons are pretty picky about how they fill these addresses. They follow some very strict rules. First, they always fill the lowest energy spots first, like water filling a bucket from the bottom up. Second, no 2 electrons can have the exact same address, which means each orbital can only hold 2 electrons and they have to have opposite spins. And finally, when there are a bunch of empty orbitals at the same energy level, they'll each take an empty spot before they start pairing up. It's a bit like people getting on a bus. Most of us will grab an empty 2-seater before sitting right next to a stranger.
So there you have it. Our picture of the atom has gone from a simple, solid object to this dynamic, bizarre, and frankly beautiful quantum system. It's a tiny, dense nucleus surrounded by these buzzing clouds of probability. It's a journey that took us from the comfort of certainty to the elegance of uncertainty.
And that leaves us with one last mind-bending question. If everything, your hand, the table you're sitting at, all of it, is made of atoms that are almost entirely empty space, why does anything feel solid? Why doesn't your hand just pass right through the table? The answer lies not in the stuff itself, but in the powerful forces between those electron clouds. A wild reminder that the strange quantum rules aren't happening somewhere far away. They're what's holding our entire world together.